Hey there, classes. Today we had the guest scientist pop on by doing a lesson on density. Just going to go over some of the things that we did in class today and why density. In other words, why do we see it so much in this class? It keeps popping up again and again. And at first, when the students came in, I reminded them that tomorrow, being Friday, we have our quiz. And our quiz is not totally open note. You can use one page of handwritten notes. Anything that you've written is fine for the quiz. And if you turn that in with the quiz, you get yourself an extra 2 points. So it's worth it to go through and write out the notes. I found that not only do the high schools do this, but also just by the fact of writing those notes, you're reviewing what we've done in class. Also look online, and we've got a study guide out there. Also try and put together a little quick video on the study guide in terms of what we did in class. Everything that's on the first page of that study guide is what's going to pop up on tomorrow's quiz. All right, getting into density here. It's one of those things where you have density being mass divided by volume. It pops up again and again. For example, we saw the density of our entire planet, 5.5 grams roughly per cubic centimeter. That means if you take a typical piece of Earth on average now, it's going to weigh about 5.5 grams for every cubic centimeter, every tiny little cubic centimeter. But as we're going to see here in class, we've already touched on it a little bit. When you weigh a typical rock at the surface of the Earth, say granite, it's only about 2.8, 2.9 grams per cubic centimeter, 2.7 sometimes. The point is it's less dense than the average density of Earth. This tells us something about the structure of our planet. It tells us that down deep in the Earth, there's got to be something much more dense than the average rocks that we find here at the surface. We're going to do a lab next week when we get back after Thanksgiving, get back here, where we estimate the weight of the boulders that are out in the quad out there. But the point is that extra mass, that density that's in the center of the Earth, that's down deep in our Earth, the most likely candidate, of course, is metal. Spinning metal gives us a protected magnetic field. And earlier this year when we were studying Mars, we were checking out the Martian. We were looking at the habitability of Mars compared to Earth. This is one of the things that make Earth a tremendously wonderful biosphere. We've got a protected spot, and we've talked continually through this year about the things that make Earth perfect for life. And when they're talking about exploring Mars, that is fantastic. We should be out there exploring our solar system, learning all we can about the planets that go around our sun, but also keep in mind when they talk about things like, oh, we're going to move colonies over to Mars. No, if Elon Musk wants to go to Mars and live there, good for him, great. But we've got a biosphere that is 4.5 billion years in the making. We've got a protective magnetic field. We've got all the things here, our biosphere, that make life a perfect place. That's what we're learning about in this class, the things that we need to do to protect what we have underneath our biosphere that is shielded, amazingly, above us by metal churning miles below our feet. If you look at good old-fashioned things that we should have on our notes, how to calculate the volume of a rectangular prism, length times width times height, of course. And also don't forget to have in your notes, and also it's in our binder reminders, the volume of a sphere. A couple other places that we see density pop up in class. It pops up all over the place. Let me get the other board over here. But one of the places that we see it is water. When you check out the density of pure water, and I'll spin my camera just a little bit, the density of pure water is 1 gram per cubic centimeter. Very, very convenient, easy number to remember, 1 gram per cubic centimeter. This, earlier in the year, so this is all review, this gave us a review that, hey, 1 cubic centimeter is exactly the same thing as 1 milliliter. Again, metric system makes it extraordinarily easy to convert between units, and it makes it easy when you're doing measurements. When you check out salt water is slightly more dense than fresh water. This is going to be especially important when we look at ocean currents, especially when you look at global climate change, and especially human-induced global warming, where we have glaciers melting at an accelerating pace. You've got fresh water being dumped into the ocean in places like Greenland over salt water. When you talk about these density differences, we're talking about changes in ocean circulation patterns. And again, this is where density, or understanding of density, is important to understand how the human impact on the environment is changing ocean circulation patterns. That's very, very big, because once ocean circulation patterns change, weather changes. And we want to pay particular attention to that. We're looking at climate and the atmosphere. Plate tectonics is driven by density differences. When you're looking at plate tectonics, a lot of scientists think that you need plate tectonics for complex life because it's a constant recycling of material. And again, these plumes of less dense material, because they're hot, remember density, when you have a hot material, I was going to draw it on the board, but I can explain it right here. When you have a less dense material, because of the heat, the molecules have greater kinetic energy, they move farther apart, the density drops. That is, again, tying back to our oceans. Another reason why the ocean levels rise as the temperature rises. It's not just the ice melting from glaciers and pouring more water into the oceans, but the average kinetic energy of the water around the planet goes up. As the average kinetic energy goes up, the individual water molecules are further apart. If they're further apart, the ocean level is going to go up. So that's one of the things that we talk deeply about in another couple of units when we are talking about global climate change again and the way the water is rising. It's not just about pouring more water into the oceans. It's about the increasing kinetic energy of that water. And then finally down here, we check out plastic pollution. Most single-use plastics float when you're talking about those big gyres, most famously, of course, the Pacific Gyre between here and Hawaii, the large circulating plastic raft of garbage that's out there. That's going to be important for the impact on the ocean ecosystem and the impact on our oceans as a whole. When we're talking about an oceans where by the time the students who are seeing this are my age, plastic will likely outweigh plankton in our oceans. And then finally down here, when we get into human physiology, one of the things I did way back in high school and college doing track, they weighed us in a tank right up the hill here at Skyline College is one of the places I did it. They weigh you in a tank where you let go of all the air in your lungs, and they see how much you weigh underwater versus how much you weigh above the water, and they're trying to tell your percent of body fat. Very, very important when we check out physiology, and this is kind of the fun part when we get into the sports science later on. Depending upon your sport, you're kind of shooting for a different percentage of body fat versus muscle. For example, runners tend to have very, very low body fat. They don't want to carry any extra weight along. If you look at force mass acceleration, you could tie in with Newton's second law there. But if you look at swimmers don't necessarily want a very low body fat. In other words, swimmers want to be neutrally buoyant. They want to be able to put all of their muscular energy into propelling themselves through the water. So swimmers tend to have a slightly higher body fat percentage than, say, runners. And again, when you're talking football players, volleyball players, there are ideal ratios of fat versus muscle. And fat gets a bad rap. Fat is very, very important. It's an energy source, of course. It is buoyant. And we're going to be talking in physiology in the spring about the percentage of body fat you kind of want to shoot for your particular sport if you have a bent on playing one of those in high school. All right. Went through it quickly. Look for the study guide for the quiz online, and make sure you check out the notes that we'll put up there from today's scientist visit, where they're having the students, reach down here and grab one right here, they're having the students make little foil boats. They're putting density cubes in there, and they're seeing how much can the boat support before its density goes above that magic number of 1 and sinks. All right, have a great day, everyone. See you online. Bye-bye.